If you can find your packet that I've posted online, that would be fantastic, just to be clear where that's posted. If you log on to Portal, and let's see here if I can remember my own password. Logging in. I've got the packet posted for you guys here. And so if you navigate to the current topic folder, which is down here, Unit 8, and right here, Handouts for Students, that's where you can find this packet. Okay, so once you've opened up the packet, you can follow along, and we've actually already looked at this page together here. So let's see if I can get this zoomed in. Let's see, view, page width. Okay, so we've already had a look at this handout, and we talked about the different types of electromagnetic radiation that there are, and that visible light is only a small part of the spectrum of electromagnetic radiation. So again, that key word is electromagnetic radiation, and that's the scientific term for light. Okay, and I abbreviate that EMR. Okay, so there's all sorts of types of light, and we talked about the different types. Something that I do want to point out is that all light moves at the speed of light. And so that equation that we saw last week, speed equals wavelength times frequency. Now it's a very specific speed, the speed of light, and c is the special symbol for the speed of light, 3.00 times 10 to the 8th meters per second. Okay, so 300 million meters per second. And so all of this stuff in this picture travels at that speed, the long wavelength stuff and the short wavelength stuff. Something else to point out that we're not going to talk too much about in regular chemistry, but we did in honors chemistry, is that light is also made up of photons. And photons are little particles of light which have zero mass. And so that's kind of strange to think about a particle that doesn't weigh anything at all, but that's exactly what photons are. So all this stuff is made up of photons, which are little particles of light. And in this packet, actually, on the next page, you'll see that there is a way to calculate the energy of a photon, and we did that in honors chemistry, but we're not going to focus on that in regular chemistry. Okay, but I did mention that this stuff over here is the energetic stuff. The further we go this direction, the shorter the wavelengths become, but the higher the frequency. So this is a higher frequency, so it's oscillating more and more quickly, and the higher the energy. And it's actually per photon, so each little particle of that light is more and more energetic. And this direction, you can see we're getting longer wavelengths as we move down toward radio waves. And this is lower frequency. These things oscillate much more slowly. And turns out that gives them a lot less energy as well. So an individual photon of a radio wave has less energy than a gamma ray photon. And if you haven't already done number 2 and number 3 here on this page, I'm not sure how far we got in regular chemistry, but that might be a good idea to check on those, and then you can look online to verify your work. But we're going to actually move on now to talking about what is coming off of the sun. So if you take a prism and you let some sunlight shine through a prism, let me show you what I'm talking about. I should have a little picture of a prism somewhere in my files. Let's see. I'm sure you've seen a prism before. Let's get a list And it should just be it's a sound wave visual. Let's see. Sort these by file type. Got some JPEGs here. I mean, this will do the trick. I took a picture of some sunlight that was coming through a prism, and you can see that you get a full rainbow of colors when sunlight passes through a prism. And so this is a little device that breaks apart the light into what the light is actually composed of, and you get a full rainbow. And if you put that on a scale where you actually see the wavelengths of light, visible light goes from about 400 nanometers to 700 nanometers, and we've already talked about that. But visible light, you get a full rainbow of colors. Now, at some point in the 1800s, some scientists discovered when you heat up specific elements like hydrogen or sodium or neon, you don't get a full rainbow of colors coming off of them when you pass their light through a prism. You only get very specific colors of light. And in fact, no matter what you do to the element, so let's say we're talking about hydrogen, you can't make hydrogen emit any other colors of light than these 4 colors of light. So we've got this red wavelength and this kind of aqua looking wavelength and a couple of violet wavelengths down here. But you don't see any yellow or orange or green. And no matter what you do to your sample of hydrogen, you can't make it emit those colors of light. And scientists thought that was really curious. If you take a different element, like neon, you know, you're probably familiar with neon lights. They glow kind of orangey and reddish looking. But no matter what you do to a sample of neon, you can't get it to emit any other colors of light than these ones here. Now, of course, this is a lot more wavelengths of light, but there are all these gaps where there's no colors. And sodium, huge gaps, and you have this one kind of prominent yellow line. And so when you heat up these elements, you only get these specific colors of light, and that's very different than sunlight. And so scientists were, definitely interested in what might be happening. And a scientist named Niels Bohr focused on the hydrogen colors of light because hydrogen, hopefully you remember, is the lightest element. It's element number 1. It only has 1 proton and 1 electron. And he thought maybe there's something going on inside the hydrogen atom that could help us explain why we're only getting these 4 colors of light. So I want to talk about Niels Bohr's model of the atom. Okay, so Niels Bohr, not going to talk too much about who Niels Bohr was, but he's a scientist who was on good terms with Ernest Rutherford and Albert Einstein and some others. And so he came up with a model for the hydrogen atom. And he went with hydrogen because it's the simplest element if you think about it. There's only 1 proton and 1 electron inside the hydrogen atom. And so he thought maybe that perhaps these specific colors of light that we're seeing here for the hydrogen, it's emission spectrum. When you heat up hydrogen, you only get 4 colors of light. He thought that maybe hydrogen atoms, the structure of the hydrogen atom would help us understand what's going on here, okay? And so first of all, he recognized something important, which I've mentioned in passing, that as these colors of light change, the energy changes, okay? So for instance, violet light is more energetic than red light. So this is the red light over here, and you have the kind of the full rainbow of colors. Whole Roy G. Biv type of thing here, and so violet light is more energetic than red light because it's further along this direction. It's got a shorter wavelength than red light, and so Niels Bohr's Niels Bohr had this insight that these different colors of light that we're seeing from hydrogen's emission spectrum, it's interesting you're getting these different colors, but he really realized these are 4 different energies of electromagnetic radiation, 4 very specific energies. Okay, so he observed that these 4 distinct colors of light in hydrogen's emission spectrum that corresponded to 4 specific energies. Okay? And I'm sure other people understood that, but he started imagining that if you started off with the hydrogen before you put any energy into it, you could sort of imagine the hydrogen atom and its energy, and before you do anything to it, the atom, so this might be a hydrogen atom, and this kind of represents some energy levels, and right here this would be the ground state. And so hydrogen atoms start off in their ground state, and then if you put in some energy, if you add some electricity or some heat and you add in some energy, so we sort of energize a hydrogen atom, the hydrogen atom would jump up from its ground state, but it would jump up to a very specific allowed energy, maybe somewhere up here. So the hydrogen atom would jump from its ground state up here, and now it would be kind of in an energized state. And Bohr called that an excited state. And he imagined that there's very specific excited states that are allowed. Okay, so those other blue lines that I've drawn there would be other allowed excited states. Okay, but for the moment it's just up into this first excited state. And the hydrogen atom's not going to stay there. It's going to relax, and it's going to return to its ground state, which is its lowest energy state. And when it does that, it's going to release a photon of a very particular amount of energy. Okay, so this difference in energy right here is going to actually turn into a photon. Okay, and that photon has the exact difference in energy between these 2 energy levels right here. Okay, and perhaps that gives you a red photon, because red photons have a very specific amount of energy. Okay, and so let's imagine you have another hydrogen atom, also in its ground state. But if you put in a little bit extra energy, you could excite it from its ground state up to this second excited state. Okay, so going from the ground state up to the second excited state, because here's the first one and here's the second excited state. And the atom doesn't stay there, it's going to relax and it's going to fall back down to its ground state, or at least to some other lower energy state. But now you see it's fallen from a higher distance. There's a greater difference in energy here, and this difference in energy corresponds to a higher energy photon. And perhaps this time it's something, let's see, I don't quite see the aqua color that I'm looking for here. Maybe something like this. Right now, we've got a photon of a different amount of energy. Still a photon, it's still a particle of light, but this photon has exactly this new change in energy, which is a very specific change in energy. Okay? And so there's other things that might happen, right? If you get excited up to the third state, we imagine another hydrogen atom, for instance. Maybe you excite the atom up to the third state and it falls back down. Well, now it's falling even further, and in that case, it might be one of those violet photons that we've, come on, trying to get some violet color here. There we go. That might be one of the violet photons, okay, with a greater amount of energy. Okay, so Bohr had this idea that within the hydrogen atom, there are these specific energy levels. The lowest energy level is the ground state, and then you have these other excited states, but the excited states are at very specific places. So the ground state, that's the lowest energy state. For an atom. And then the excited states are at very specific spots, kind of like steps on a staircase. And they're sort of set energy levels in an atom. And he thought maybe that could explain these particular colors that are coming off of the hydrogen when you excite it. Okay. And the more that he thought about this, the more that he realized these excited states might have something to do with the electron inside of the atom. Okay, so now we really are going to get into Niels Bohr's model of the hydrogen atom, because these little energy diagrams are a little bit abstract and they don't look anything like atoms. So he's really trying to figure out the structure of the atom. Okay, so he brings it all together here and he imagines inside the hydrogen atom that these little excited states in the ground state have to do with orbits. So he imagined, so Bohr imagined that the electron in the hydrogen atom moves at distinct, specified, allowed, which is sort of a weird word to use, orbits. Okay, so remember Rutherford's model of the atom was, he wasn't really sure about it, but Rutherford kind of thought that, here's your nucleus and then the electrons just kind of orbit wherever, right? Just kind of buzzing around the nucleus, okay? And so Bohr says, no, that's not right. There are very distinct spots, distinct orbits for the electron. So here's your nucleus, and then out here, maybe this is your first allowed orbit, and here's your second allowed orbit, and your third allowed orbit. And I'm not doing a great job drawing these as really circular, but hopefully you get the idea. You have these specific allowed orbits. Okay, so as the electron is orbiting, imagine that it's right here. So there's our little electron. And maybe I can zoom in a little bit and let's see. Try to zoom in a little bit. There we go. I think that's all I can do. All right. So here, maybe our electron is on that first orbit. Okay. But if we add in some energy, so energy in the form of electricity or something like that, we can cause this electron, which is orbiting, to jump up to the next orbit, okay? So it's moved up to the next orbit. It kind of just jumps up like if you were jumping up the stairs. Okay, it's not going to stay in that second orbit. Eventually it's going to fall back down. And when it does that, it's going to release a very specific amount of energy. Maybe that's that red photon that we saw in its emission spectrum. Okay, so we get that red photon, so a little packet of energy. So a photon is basically like a little packet of energy. Okay, all right, so this sort of makes sense. Imagine if you're holding, if you've got a bowling ball on the second stair of a staircase and you roll it down to the first stair, it's going to make a sound. It's going to smash into that lower step and release some energy in the form of sound. And Bohr said when electrons fall down from a higher orbit to a lower orbit, they're going to emit some energy too. But that energy is not a sound wave, it's a photon. Okay, and of course we can imagine, what if we cause that electron to jump up a little higher? Well, then it would fall down a little bit higher and it would release even more energy. So in that case, maybe it's that aqua photon that gets released. It's a little bit more energy, higher energy photon. And so on and so forth. We have these distinct orbits. And so maybe just drawing in one more, if we can get that electron to jump up from the first energy level to the fourth energy level, right? Well, then it falls back down to the ground state orbit, and that might be one of those violet photons, okay? And so on and so forth. So that's the whole idea behind the Bohr model of the atom. It's to make sense of what we're seeing here in the hydrogen spectrum, okay? Only specific colors of light are being emitted. And so the whole idea is there's got to be specific energy levels inside the hydrogen atom. Okay, so a couple comments about Bohr's model, and then we'll be done for today. So Bohr's model worked really, really well, but just for the hydrogen atom. He wasn't able to succeed with any other atom. So here we go. Bohr's model made sense of the data for the spectrum, the emission spectrum of hydrogen. But only for hydrogen. He had a lot of trouble figuring out the spectra of the other elements. So even for sodium, it doesn't look very, very complicated, but then again, there's a lot of other violet and blue lines going on down here. Neon's really complicated, and then something like tungsten, when you heat up tungsten, you get a lot of different colors of light. And so hydrogen was fairly easy to explain because there's only one electron in the hydrogen atom. But in sodium, you've got 11 electrons. In neon, you've got 10 electrons. And in tungsten, you have 74 electrons. And it's not obvious why you have all these different colors. Like sodium has a simpler spectrum than neon, and yet it has an extra electron. So that's not really following a clear pattern. But at any rate, Bohr's model of the atom works perfectly for hydrogen. And he's able, actually, using his model, he's able to determine the approximate size of these orbits based on calculations of something called the angular momentum of the electron. When things are spinning around and rotating, if you imagine you've got a golf ball tied to a string and you're just spinning it around overhead, the golf ball has something called angular momentum, which in physics you can calculate. And so Bohr actually does this with the electron, and his calculations line up perfectly with the colors of light, this red and this aqua and violet and the other colors of light that hydrogen emits. So his model works really, really well. And so he's really onto something. He seems to be onto something. And the something that he is onto is that there are quantized energy levels in the atom. Quantized means kind of like a staircase. Okay, to illustrate what I mean by that, imagine you are walking up an inclined plane. So if you start down here at the bottom of an inclined plane, that's just like a ramp, and you're moving up the inclined plane. There's literally an infinite number of places you could stop. Okay, you can stop wherever you want as you go up an inclined plane. You could stop here, you could stop there or there. Okay, there's an infinite number of places you can stop. Oops. But if you have a quantized, this is called a continuous scale. It's continuous. But if you have a staircase, right, and you're walking up the same height, there aren't really an infinite number of places you can stop. If you're down here, and these, of course, are some really big stairs, you have to kind of hop up. There's not an infinite number of places you can stop. You know, if you're going to stop and rest for a moment, you have to be on a step. You know, it's got to be somewhere on one of these steps. You can't stop here, for instance. It's not a stable position. Okay, so that one is not allowed, right? Not allowed. You have to be on a step. And this is called a quantized scale. There are allowed places to stop. Okay, and that's called a quantized scale. Okay, so that's what Bohr was really onto with his model of the atom. So go ahead and stop the video and navigate to the assessment and answer the questions there, and you'll be done for today.